So in this video, we're going to focus on the first two items here. We're going to determine continuity of functions, and we're going to determine the continuity of functions on a closed interval. So three things are happening here with continuity. In continuity, we have three things that must happen. At x equals c1, f of c1 is not defined. Okay, so that's a situation. Another would be at x equals c2, the limit as x approaches c2, f of x does not exist. So here's c2, and the limit does not exist because we have from the left, let me use blue, from the left, from the right, we're approaching two different values. So the limit does not exist. The overall limit does not exist. And then 3, so let me show you on this picture what's happening here. 3, at x equals c3, I'd like to pick some pretty colors here, orange. The limit from the left equals the limit from the right. However, the limit does not equal the function value. So that's what this one is saying. The limit does not equal the function value. So we're talking about continuity. And this graph is not continuous for a variety of reasons. There are three varieties right here. 1, 2, and 3. So as I go from left to right, you can think of this as if I have to pick up my pencil, then it's not continuous. So as I come here from left to right, look, I have to pick up my pencil, hop over the hole. That means, that's actually not an arrow right there. That's a point, right? That means that I'm discontinuous. But algebraically, why is it discontinuous? It's discontinuous for reason number 1. Because the function is not defined, you have a big gaping hole. The next one, okay, here the function is defined when x equals c2, but there's a jump. So you jump from this higher value to this lower value. You have to pick up your pencil and jump. That would be reason number 2. So a jump in your graph. And then this third one, now this third one, we also have the function is defined at c of 3. However, the limit exists, right? So on number 2, the limit didn't exist. On number 3, the limit exists, but the limit doesn't equal the function value. So this was reason number 3. The limit does not equal the function value. So all three of those reasons are reasons why a graph would be considered discontinuous. Now, they have a nice picture of a pencil here because that's really what it is. The definition of continuity is if I can draw from left to right without picking up my pencil, then I've got continuity. And there is continuity on this open interval. So on this open interval, this is A right here, and this is B. This is an open circle. This is an open circle. From A to B, we have continuity. A function is continuous at the point C, any point C in between. So here's C, and I'm going to move C left to right. So C can be at any point in between A and B. The definition of continuity says the function is continuous at the point C if all three of these conditions are true. So all three of them have to be true, not just one, but all three. First of all, f of c is defined. Okay? So if c is right here, then f of c has to be defined. Number 2, the limit as x approaches c of f of x exists, which means, this is very, very important, which means the limit from the left equals the limit from the right. Okay, so the limit from the left has to equal the limit from the right for the limit to exist. So over here, the limit exists on the left, it exists on the right, and they are equal to each other. Therefore, the limit exists. That would be number 2. Number 3 now combines 1 and 2. So number 3, so here's number 2, here's number 1. Number 3 says that number 1 equals, that's the part of number 3. Number 3 is this equals to. Number 1 equals number 2. All 3 of these things have to happen. So first, your function is defined at x equals c. 2, the limit as x approaches c exists. And number 3, f of c equals the limit. And then you have a continuous interval from a to b. So sometimes we look at functions in which the entire function is continuous, and sometimes we're just looking at a portion of the function. Now, there are 2 types of functions where direct substitution can be used. We learned this in our previous lesson, in which you could just go straight to direct substitution, and one of those is the polynomial function. It is continuous at every real number. Remember, I used the words smooth and continuous. Polynomial functions are smooth and continuous. Okay. Another one that's going to surprise you are rational functions. Rational functions are also continuous, but in a very specific place at every real number in its domain. Okay. So rational numbers, they have that additional stipulation. Continuous at every real number in its domain. Okay. Polynomial functions, continuous at every real number because every real number is the domain. So you could think of these 2 as the same. The polynomial function, the rational function, they are continuous at every real number in its domain. It just so happens that the polynomial function, every real number on the number line is in its domain, negative infinity to positive infinity. There are no asymptotes, there are no holes, nothing like that. Okay, so let's determine continuity of a polynomial function. Well, we just said what the continuity is. Polynomial function is continuous at every real number. So what I'm going to do on each one of these is I'm going to list the domain. This way I'm consistent. List the domain. The domain is negative infinity to positive infinity, and it is continuous from negative infinity to positive infinity. B is also a polynomial function. Its domain is negative infinity to positive infinity, and it is continuous over its entire domain, negative infinity to positive infinity. What 2 functions are continuous over their entire domain? What functions are continuous over their entire domain? Well, the answer to that is polynomial functions and rational functions. And polynomial functions have a domain of negative infinity to positive infinity. Here's a study tip for you. I like these study tips that are in the book. F of x equals x cubed plus 8 over x plus 2. F of x equals x plus 2 over x squared minus 2x plus 4 over x plus 2. X cannot equal negative 2, so the domain of this function the domain of this rational function is negative infinity to positive infinity, and it is continuous over its entire domain of negative, I don't believe I just said that. It's not negative infinity to positive infinity, it's negative infinity to negative 2. I think I'm thinking about lunch right now. Negative infinity to negative 2, negative 2 to infinity. And it's continuous over that same domain. So there you go. So determining the continuity of a rational function, we're going to do the domain and the continuous interval for each one of these. So A, the domain of 1 over x, the domain is negative infinity to 0, 0 to infinity. And it is continuous over that same interval, negative infinity to 0, 0 to infinity. B, I'm going to rewrite B, x squared minus 1 over x minus 1, that's f of x. The domain for B is negative infinity to 1, 1 to infinity. So it's going to be continuous over that same interval, negative infinity to 1, 1 to infinity. And C is 1 over x squared plus 1. Its domain is all real numbers because there's nothing you can put in for x, square it, and get a negative 1. Not in the real number system. So we would have anything plus 1 is positive, right? Anything times itself is going to be a positive number other than 0. And even 0 plus 1 is positive, which means you'll never get a result of 0 in the denominator. So the domain is negative infinity to positive infinity, and it would be continuous from negative infinity to positive infinity. Now, why is that the case for all three of these? Because all three of these are rational functions. So this happens with a rational function, and this happens with polynomial functions. Why is that? Because of this part right here. What functions are continuous over their entire domain? And it is polynomial and rational functions specifically. Okay. So now you try, and when you're ready to check your answer, come on back and check your answer. Okay, hopefully you did all three of these problems. You really thought about it, and you're ready to reveal whether or not you have the same answer I have. So let's do a quick reveal. I got continuous from negative infinity to 1, 1 to infinity for A, negative infinity to 2, 2 to infinity for B, and negative infinity to infinity for C. Beautiful, 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 beautiful. So there's two different types of discontinuities. We have discontinuities that are wholes and discontinuities that are vertical asymptotes. So you might remember from college algebra, you've got a removable discontinuity. A removable discontinuity is a whole. That's when you have common factors. This is a big idea in college algebra. Non-removable discontinuity. So non-removable discontinuity is a vertical asymptote. A vertical asymptote. No common factors exist. And when you're done reducing everything, you still have that value in the denominator that causes a problem. That is your vertical asymptote, and that is a non-removable discontinuity. So I'm going to come back here real quick, and we're going to identify these. Number one would be non-removable. So in this graph, you would have a vertical asymptote. In the next graph, this would be a removable because the x minus 2 cancels out. So that's removable discontinuity at x equals 2. And that, the graph would be a hole in that position or in that section, that particular area of the graph. And this last one, there is no discontinuity, which is why we have from negative infinity to positive infinity. It's a beautiful thing. So let's talk about definition of continuity on a closed interval. So continuity on a closed interval. Let me try and draw a picture of this for you, what they're saying. And then you can go back and look at the definition. So we've got this graph, and we'll just call this A, and we'll call this B. And it's going to be a closed interval, which means A and B are included. And I'll just make it look something like that. Okay, so we have continuity happening, right? So we've got continuity happening because I don't have to pick up my pencil. So from left to right, I just, boom, this is like a section of a polynomial function perhaps. This is going to be continuous. So my domain, let's start with the domain. The domain is A to B. This is not a polynomial function, and this is not a rational function. This is a chunk of some kind of graph where the domain is a closed interval from A to B. However, it is continuous on the open interval A to B. So let me explain to you, maybe you can even think about it based on our definition. Why would it be continuous on an open interval and not continuous at A and B? Well, if we look at A, f of A is defined, right? The limit as x approaches A exists from the right, but does the limit exist from the left? It doesn't. So the limit does not exist from the left of A. That's why we've got this right here. The limit as x approaches A from the right is equal to f of A. And this one over here, if we look at B, the limit coming from the left exists, and it equals f of B. However, the limit doesn't exist on the right. Therefore, we're going to have continuity on an open interval A to B. Okay, so it's going to be continuous from A to B. We're also going to say that it is continuous all the way because the domain is continuous from A to B. So let's examine continuity at an endpoint. Let's look at continuity from the endpoint. Now, let me come back here and let me just explain one more time. So it's continuous from between A and B, but because this is a closed interval, right? So it's continuous from A to B, we're going to say that the domain is continuous. We're going to say the function's continuity will include the endpoint. So it will include the endpoint. For this given situation, the function's continuity will include the endpoint and therefore will be A to B. So this is the continuity. This is the domain's continuous continuity. Okay, this is the function being, this is the functional, the continuity of the function, and this is the continuous of the, this right here in green is the continuous of the domain. I don't think I was real clear about that. So let's come over here and I'll show you. Let's see if I can, I don't know what I'm doing here. Let's undo that. There we go. There. Okay. So let's think about this graph. We've got f of x equals the square root of 3 minus x. So this is a reflect over the y-axis, and then it's going to go right 3. So 1, 2, 3. And it's going to look something like this. See, when we know our parent functions, it makes it pretty easy to look at this. So now we've got a domain from negative infinity to 3. Between negative infinity and 3, our domain is continuous. So our domain is continuous from negative infinity to 3. And our graph is continuous, meaning we don't have any breaks, so no breaks, no jumps, no holes. I'm going to say pencil perfect, meaning you don't have to pick up your pencil when you're drawing it. So let me show you. So you don't have to pick up your pencil just keeps going, boom, 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 close it in, never had to pick up the pencil. So this function with respect to its continuity goes from negative infinity to, now when we look at the endpoint, we have to make sure that the limit is equal to the function value. So when you're going to this endpoint right here of 3, you have to make sure that the limit as x approaches 3, in this case from the left, is equal to f of 3. And it indeed is. So the continuity is negative infinity to 3. Okay, you go ahead and try this one, and when you're ready to reveal, go ahead and press play. Okay, let's check your answer. This is continuous from -2 to infinity. And -2 is included because this time our graph is going to the right, so our limit as x approaches -2 from the right is equal to f of -2, which happens to be that point right there. So that's why -2 is included, and we consider this function to be continuous from -2 to infinity. So hopefully you're feeling pretty good about that, enough that we can maybe go to a piecewise function. So we're going to graph this piecewise function. I'm going to graph 5 minus x from -1 to 2. So when I put a -1 in, I get a 6 out, and that's a closed circle. And then when I put a 2 in, I get a 3 out, 1, 2, 3. And that's a closed circle. And this was a straight line, so I'm going to connect those. X squared minus 1, that's a curve. When I put, so sorry for that. When I put a 2 in, it's going to be an open circle. 4 minus 1 is 3. But the closed circle fills the open circle, And then when we put a 3 in, I get an 8 out. So this is going, and that's a closed circle. So this is going to be a curve right here. So we're talking about continuity. So what is the continuity of this function? Well, we know that the domain goes from -1 to 3. But are there any jumps? Is this continuous from -1 to 3? So are there jumps? Are there holes in which there would be a jump? So one has a hole, but then it jumps up and fills it in so that the domain is continuous, but I have to pick up my pencil. The answer to this is no. See, look, I don't have to pick up my pencil, and I can draw that graph without picking up my pencil. So now we have to look at this particular place right here. So let me get my color. Let me do red. So I have to look at where x equals 2, because that's where one function ends and the other begins. What is the limit? What is the limit? And what is the function value? And it's g of x, not f of x. Well, g of 2 is equal to 2. And the limit as x approaches 2 from the left of g of x is equal to 2. And because it's in the middle and we're not talking about an endpoint, the limit as x approaches 2 from the right is also 2. These two are equal to each other, which is very important because we're in the middle of the graph, not at the endpoint. The limit exists. The limit equals the function value. This indeed is continuous. From -1 to 3. So what was our first thing that needed to happen? So remember, f of c had to be defined. F of c is defined. So g of 2 was defined, because that's going to be the critical area right there, because that's where the two graphs meet. And then what had to happen was the limit as x approaches c exists, and it did exist right there. It existed because the left equaled the right. And then what had to happen? 1 had to equal, not equal, step 1 had to equal step 2, and that sure as heck happened right here. So 1 had to equal 2, and that happened right here. This limit was 2, and it equaled that 2, and there you go. Okay, let's do one more as a try and see if you've got it. We're going to continue to practice this step 1, step 2, step 3. It's going to take some practice because it's very important that we know all 3 steps. So go ahead and see if you can graph this, and then we'll talk about step 1, step 2, step 3. Okay, so I'm not sure if you had a heck of a time drawing this, but I did, because I ran out of room. So boom, you get the idea. It's going to drop, it's going to be curved, it's going to drop. Just make it thick enough. Nobody knows, right? It's all about where x equals 3. That's where we're going to have to be concerned, because that's where one piece ends and the other begins. So we're looking at this particular point right here. We know that everywhere else, we know in this highlighted green area, we've got continuity, we've got continuous stuff going on. We know that in this blue area we do, but it's where one graph becomes, where one piece changes and another piece takes over. That's where we have to be concerned with whether or not we have a jump or a break in our graph. Well, there is no break in the graph. So now we're just talking about what is f of 3. Is it defined? It absolutely is defined. It's defined to be 5. What's the limit as x approaches 3? Well, the limit from the left is 5. The limit from the right is 5. So the limit as x approaches 3 of this graph is also 5. Because the function is defined at x equals 3, because the limit exists as x approaches 3, and because those two equal each other, that means at this potential problem point, this is your potential problem point. Everywhere else we know is not a problem. This is your potential problem point. Because this potential problem point has those three things happening, step 1, step 2, step 3, this is not an issue. We've got continuity, and this is continuous from -1 to 5 with an open circle. And I think that my graph did not have that open circle at the end. There it is. There's the graph, the open circle. And the reason it's an open circle is because, nope, it's a closed circle. Therefore, it's a bracket. I thought that I didn't realize that this equal to sign. There we go. It's a bracket. Right there. Bracket. 5 is included. Done. This is your continuity right there.